Welcome to this explainer. Okay, so today we're diving into something that's honestly a massive shift in how we actually build AI. For the longest time, the strategy has just been, make individual models bigger, feed them more data, rinse and repeat. But researchers are now looking at something totally different: how to turn these isolated models into a beautifully orchestrated team. So let's jump right in and see exactly how they're pulling this off.
Here's a quick look at our roadmap. We're going to start by looking at the limits of single models, then introduce this new RL Conductor, break down how it actually uses natural language to coordinate, check out some really impressive benchmark data, and finally wrap up with recursive scaling. All right, part 1. Let's talk about the single model limit. Let's be real, we're living in an era of absolute giants. Models like GPT-5, Claude Sonnet 4, and Gemini 2.5 Pro have been trained at a scale that's just unprecedented. They're showing capabilities that legitimately border on human expert levels. But here's the reality check we're all discovering. Every single one of them has blind spots. One model might be absolutely brilliant at writing complex Python code, but then completely struggle with deep, logical, multi-step planning. Another might ace graduate-level biology, but then totally fail at following strict output formatting rules. There is literally no single large language model that is universally perfect across every task. So the giant question the whole industry is facing right now is, how on earth do we best combine their unique strengths? Well, until now, our options haven't been all that great. You either rely on what we can call the soloist, so a single language model just trying to do absolutely everything by itself, or you try to stitch them together using these rigid, human-coded frameworks, kind of like the mixture of agents approach. But here's the thing, building those pipelines manually, it's expensive and it is highly inefficient. The reason they're so rigid is that a human programmer just can't predict every single possible route an AI might need to take to solve a complex problem. Think of it like taking a group of brilliant solo musicians, throwing them on a stage with zero sheet music, and just expecting a masterpiece. What you actually get is a disorganized, messy jam session. The models end up confusing each other, or they just waste massive amounts of computing power on really simple problems. Which brings us to section 2, introducing the RL Conductor. Let's see how researchers elegantly fixed this coordination chaos. So the researchers introduced what they're calling the RL Conductor, and instead of relying on rigid Python loops or hard-coded routing rules, the conductor is actually a language model itself. But the truly surprising part here, it's tiny. We're talking just 7 billion parameters. When you compare that to the massive trillion parameter giants we were just talking about, it's remarkably small. And that's because its job isn't to solve the complex math or coding problems directly. Its entire purpose is to dynamically break down the problem, delegate those targeted subtasks, and design exactly how the worker agents communicate with each other. And it does all of this using pure natural language. It essentially acts as this super clever meta agent that sits above and controls the really heavy-hitting frontier models. Okay, so you might be wondering, how did it actually learn to do this? Well, the researchers didn't spoon-feed it thousands of human-written templates. Instead, they used a reinforcement learning algorithm called GRPO, or Group Relative Policy Optimization. Basically, in plain English, that means pure trial and error on the fly. They just gave the conductor a problem and said, hey, figure out how to use these other models to get the right answer. The conductor only gets a positive reward if the final group project gets a passing grade, meaning the workflow has to be properly formatted and the final answer from the worker agents has to be completely correct. By trying to maximize that end-to-end reward, the conductor organically discovered these incredibly powerful coordination strategies completely on its own. All right, moving into section 3, let's peel back the curtain and look at how it actually orchestrates with natural language. For every single step in its workflow, the conductor outputs 3 really simple things. First, it writes a natural language subtask, basically custom instructions for the exact piece of the puzzle it needs solved right then. Second, it outputs a worker ID. This selects the specific agent that's best suited for that exact job, whether that happens to be an open source model or a massive proprietary one. And third, it outputs an access list. Now, this last piece is absolutely crucial. It dictates exactly which previous answers from other agents should be shared with the current worker as context. Tightly controlling who sees what is vital because it stops the models from getting distracted or confused by totally irrelevant information. The conductor is literally building the communication network entirely on the fly. And honestly, this brilliantly highlights the conductor's emergent prompt engineering skills. Take a look at this quote, which is directly from the conductor's output during a complex coding task. It assigns Model 2 to develop an efficient algorithm. Then it turns around and assigns Model 0 to actually write the Python implementation based on that logic. It's genuinely incredible that the AI figured out this exact separation of labor without anyone telling it to. It just naturally realized that separating high-level mathematical planning from the actual syntactic coding gives you a vastly better result than just asking one single model to do both at the very same time.
And what's really interesting here is the adaptivity. The conductor definitely does not use a one-size-fits-all approach. For a pretty straightforward fact retrieval task on the MMLU benchmark, it dynamically decides to allocate just 1 or 2 steps. It recognizes the problem is easy, so it saves compute power. But when it's faced with a really complex programming challenge on something like LiveCodeBench, it scales way up. It designs these intricate workflows with 3 or 4 steps, maybe involving a planner, a coder, and then a completely separate model acting as a final validator. It matches its computation exactly to the difficulty of the task in front of it. Let's look at section 4, because it's time to talk about the proof, the benchmark smashing performance results. The numbers here are just staggering. By intelligently combining the strengths of its individual workers, this tiny 7 billion parameter conductor beats out every single individual frontier model on the market. And we are looking at grueling, graduate-level benchmarks here. It pushes accuracy on LiveCodeBench to nearly 84%. On Amy 25, which is a notoriously brutal math competition benchmark, it hits 93.3%. And on the GPQA Diamond Natural Science test, it achieves an absolute state-of-the-art 87.5%. The collective intelligence that the conductor orchestrates just completely surpasses even the very best solo models available. But you want to know what makes those benchmark scores even more impressive? It's this number right here, just under 2.5 cents. That is the average cost per sample to run the conductor's workflows. Because it dynamically avoids unnecessary steps and writes incredibly targeted prompts, it is incredibly token efficient. Compare this to older multi-agent frameworks like MOA, which force every single model to generate an answer for every single step. Those end up costing twice as much. This massive drop in cost is a game changer because it means expert-level, multi-agent AI could very soon be cheap enough for everyday developers and small businesses to actually use, instead of being locked away for only the most massive tech companies. Finally, section 5. Let's explore recursion and what this means for future scaling. The way the conductor is built gives it a few superpowers that point to a really wild future for AI. First off, researchers found it can be quickly fine-tuned to adapt to completely arbitrary pools of purely open-source models just to save money. Second, they used out-of-distribution examples during training. Basically, they threw unexpected curveballs at it so it couldn't just lazily memorize the test and reward hack. Third, they proved that scaling the conductor from 3 billion to 7 billion parameters vastly improved its natural language prompt engineering. But the absolute most fascinating feature on this list is that last one, recursion. So recursion happens when the conductor is actually allowed to call itself as a worker agent. Look at the jump on the really complex big code bench coding task. GPT-5 Solo scores a 33.8. The standard conductor boosts that up to 37.8. But when the conductor is recursive, meaning it can look at the output of a worker, realize the strategy just isn't working, and then iteratively spawn a brand new workflow right on the fly, the score jumps to an incredibly impressive 40.0. This recursive ability essentially acts as a dynamic test time scaling axis. During evaluations, the researchers noticed something really interesting. Sometimes a usually reliable model like GPT-5 would just stubbornly ignore strict formatting rules on certain specific coding problems. The recursive conductor actively realized this failure mid-task, adjusted its workflow on the fly, and smartly pivoted to completely different agents just to handle the final code formatting. It is true cognitive flexibility, happening actively at inference time. So, to wrap up this explainer, I want to leave you with this thought. We've seen how a surprisingly small model can completely push the boundaries of frontier AI, just by acting as an intelligent coordinator for text. But if pure natural language is all it takes to orchestrate complex workflows, imagine the implications. What happens when we add workers with expertise in entirely different modalities? What happens when this exact framework is applied to orchestrate vision models, or robotic actuators in a physical factory, or even biological predictive models in a real-world lab? It feels like we're just scratching the surface of what collective AI intelligence can actually achieve. Thanks so much for joining me for this explainer.